Hi, my talk today will be about the soft actor critic algorithm by Neuer and colleagues. And first of all, you might ask, why was soft actor critic even proposed, and what is the novelty or the contribution of this algorithm to the field of reinforcement learning? And to answer this, we need to take a look at state-of-the-art algorithms back in 2018 when soft actor critic was proposed. And here on the right side, you can see other popular model-free algorithms. And of course, in reinforcement learning, we have two broad families, off policy and on policy. And the algorithms belonging to the off policy family, here on the left side, mainly DDPG and TD3, those work best with deterministic policies, but they can also use a replay buffer, but on the other hand are very brittle with respect to hyperparameters, so you need to tune those very finely. And on the other side, you have on-policy methods. And as you may know, with on-policy methods, you use a policy gradient method to improve the policy. But in order to compute the gradient for your policy optimization, you need data that comes directly from the policy you're trying to improve. And therefore, those algorithms have a low sample efficiency because they cannot reuse samples that were encountered before, but they are stable and also work well with stochastic policies, contrary to off-policy algorithms. And what soft actor critic tries to do is it tries to combine those two worlds by using an off-policy formalization and therefore a replay buffer, but also dealing with stochastic policies. Stability in soft actor critic is more of a relative notion, but we will get into this later. But I can give away that it's not as brittle as the other off-policy methods on the slide right here. And actually, soft actor critic is very similar to TD3. And if you remove all stochasticity from soft actor critic, you get an algorithm that is very, very similar to TD3. And what we're going to do throughout these presentations is we're going to derive SAC together. But since SAC is an actor critic method, as the name implies, I want to give you a brief recap of those kinds of algorithms before we start. So actor critic is basically a TD version of policy gradient, and commonly you have two networks. You have a critique network and you have an actor network right here. And the critique informs the actor. So the critique informs the actor how good a specific action that was chosen is, and the actor is learning by policy gradient, while the critique is just a value function, and therefore, of course, the critique can be a state value function or an action value function or network in our case. And in my opinion, this actor-critic interaction becomes obvious if we just derive the policy gradient for such an architecture. So we will do this real quick. And we start with the vanilla policy gradient right here. And GT is the discounted return, which is then multiplied with the gradient over the log probability over the distribution that is the policy. And what we can do, we can pull out this discounted return out of this expectation, and we end up with this expression. And by definition, the expectation over this discounted return is just our action value function, our Q function right here. So we can put everything back together in this expression right here. And as we can see right here, this is our final expression. And since this is our gradient, the direction in which our policy is updated now depends on our Q value function. So the critique, our Q value, suggests the direction in which the policy is updated. And now we can look at the complete algorithm. And here, of course, we use our actor to interact with the environment and sample actions. And then we use those actions and observe rewards. And afterwards, we just use the expression we just derived to update our policy network, our actor network parameters, suggested in the direction suggested by our critique, our Q function. And afterwards, we also need to update our critique, and we do this by the TD arrow, just as usual. So we compute the TD arrow, and we use the TD arrow to update our Q function as well. And we do this, of course, iteratively to converge ultimately. So I hope was able to refresh your memory a bit, because now we will go back to the soft actor critic algorithm. First of all, I want to highlight all tricks and features SAC uses. And as I already mentioned, SAC can use a replay buffer due to its off-policy familiarization. And next, and maybe also most important, SAC is an entropy regularized actor critic algorithm. And entropy regularization is the mechanism that is used for exploration in SAC. And this approach is based on previous papers by the authors, and namely a paper called Soft Q Learning. So this is actually where the name soft in soft actor critic comes from. And we will talk about this entropy regularization in a minute. But first, I want to mention that there are actually 3 versions of SAC. And in the first version, they used a state value function and an action value function network. But in the 2 preceding versions, they ditched the state value network because they claimed it was unnecessary. And instead, they utilized the clip double Q trick from TD3. And they also introduced an automated way of adjusting the temperature, which I will also explain later on. But let's start with the entropy regularization. So in information theory, entropy is the level of uncertainty of a random variable. And this is also roughly what entropy in the context of reinforcement learning means. So for us, it means how predictable the action of an agent is. And if a few actions have high probability, as you can see here on the left side, the agent has therefore low entropy because the agent is predictable. In contrast, high entropy leads to less predictable behavior of the agent. And this is where exploration comes in, since we want the agent to explore different actions instead of just relying on actions that return positive rewards before, because this will result the agent in getting stuck in a local minimum. So if we try to maximize the entropy of our policy, we also prevent the agent from falling into a local minimum, because the distribution won't become narrow as shown here. And here on the left side is the definition of the entropy H that will come up a lot in the following equations. And I will put this more into the context of reinforcement learning now. So in standard reinforcement learning, of course, what you do is you define the optimal policy as the policy that maximizes the expected reward. And in maximum entropy reinforcement learning, you also add this entropy term H we have just seen. So you also want to maximize the entropy in addition to the reward. And the entropy H here is multiplied with alpha, a hyperparameter. This one is also called the temperature, and it scales the entropy. And also I want to emphasize that in other algorithms like H2C that also use entropy as an exploration mechanism, there the entropy is added externally. So it's added right here externally to the MDP objective. So the MDP objective remains the same. But in soft actor critic, we include the entropy right here into this MDP objective, which changes the objective, and therefore we have to derive the equations differently. And this is exactly what we will do in the following. But to do this, I want to recap how policy iteration in the actor critic setting works. During policy iteration, you repeatedly evaluate the current policy and find the value function for this current policy. And afterwards, you want to find a new improved policy based on the previous value function. Therefore, in our actor critic setting, we want our critic right here to improve through policy evaluation, so by rolling out the current policy. And afterwards, our actor needs to improve through policy improvement, which is guided by the critique. So as a first step, we need to come up with an objective function for our critique that allows us to train our critique networks. And after this, we can do the same for our actor, also defining a loss function. So let's start with the policy evaluation step. We want to come up with a specific Bellman operator that allows us to compute the TD error and to learn the Q function. So first of all, we need to derive the value of the state, or the V function. And as I already told you, the entropy regularization changes the MD objective. So our Bellman operator or our V function is different to standard reinforcement learning. And this is obvious if you take a look at this backup diagram. And here you can see that our V function, does not only depend on Q as well as V of the preceding state, but also, of course, on our entropy. We've seen that before. So our V term right here, our V function, will be the entropy term, our H, plus the expectation over action over the Q function. This is just this path right here. And in this expression, we can just plug in the definition of the entropy. So this is just the definition multiplied by our temperature alpha. And this is just the same as above here. So we have still the expectation over actions of the Q values. And since we now have the sum of two expectations, we can just write them as one big expectation. And this is our final V function. And this allows us now to define our Bellman operator, just as usual, with our reward plus the discounted expectation over our preceding state's value. And here, of course, our V is the V function we just derived. And just as a disclaimer, don't get confused, I copied over different formulas from different sources. So the A here is a different A than here, but it still means an action. All right, now having obtained the Bellman operator, we can define the objective function for our critique network. And the objective function is just minimizing the TD error. So the error between our prediction, our Q prediction, and the observed reward plus the discounted value of the preceding state. Of course, it's squared as usual, but this is just a TD error as it's normally done. And here our V function is, of course, the one we just derived, including our entropy term that we've seen a lot now. Okay, now we are done with the evaluation step and found a loss function for our critic. And now we have to do the same for the actor. Here in the policy improvement step for standard actor critic methods, you would actually update the policy such that the policy becomes greedy with respect to the Q-value function. This means that we want the policy to choose actions that have a high Q of SA value. In soft actor critic, what they do is they use the same idea but with a trick. So first of all, the objective function for the actor is defined to minimize the KL divergence between the policy and the Q values. And if you do not know what the KL divergence is, on a high level, it describes how different two distributions are from each other. And in addition, they contrast the Q values right here by applying the exponential function on them. And this results in high Q values becoming even higher and low ones staying low. So therefore, you have a contrast between Q values. And this Z term right here is just a normalization term to make sure the right term here is a distribution with probabilities summing up to 1, because otherwise you're not able to use the KL divergence. And also this 1 over alpha is just a factor. So by minimizing the KL divergence in these objective functions between the policy and the contrasted Q values, our policy prefers actions with high Q values. And after using the definition of the KL divergence, you end up with this expression right here. And one note here, this expression here takes the expectation over the replay buffer, so D is the replay buffer, of the expectation of the action that the policy will take right here. And to sum up, we already derived the objective or loss function for our critic, and now also for our actor. But of course, if we want to train our network with, for example, stochastic gradient descent, we also need the gradient of the objective functions. And taking the gradient of an expectation with respect to a parameter is not a problem as long as the expectation does not depend on the parameter as well. And for the critic objective function here, this is not the case because this expectation here does not depend on theta, which we want to take the gradient with respect to. And here we can just compute the gradient like we're used to and get this expression right here. But if we now consider the actor objective function, here you can see that this expectation also depends on the parameter phi with which we want to take the gradient with respect to. So in order to compute this gradient, we would actually need to take the gradient of our policy with respect to phi, which has no analytical solution. So we need to come up with a clever way to make the expectation not depend on phi anymore. And in soft actor critic, they used what is called the reparametrization trick. But since we take the expectations over the actions our policy takes right here, it makes sense to first take a look of how those actions are actually computed. And for this, we need to consider the policy network. So SAC in its original form uses a Gaussian policy, of course only if our policy is stochastic. So the policy or actor network takes as an input states right here and outputs the mean and the variance of a Gaussian. And to choose an action, you sample from the Gaussian right here that is defined by the variance and the mean that was outputted by the network. And the problem is now that when sampling from this Gaussian, with a very low probability, you may end up with a very extreme value for your action. It's very unlikely, but you have to keep in mind that you need millions of samples during training. You need to sample millions of actions right here. And what you can do to prevent this is apply the 10H function onto the sampled action. And this is actually what also the authors do with soft actor critic. And this squashes the value of the Gaussian between values between 1 and -1 and prevents those extreme values from occurring. So our action that we receive from our policy is therefore the tan-h applied to the sample from the Gaussian that is provided by our network. Now that we know how actions are defined, we can use this information to solve our problem from before. So remember, we want the expectation, this one right here, to not depend on phi anymore, because we want to take the gradient with respect to phi. So this is just the definition of our action that we just defined or found out on the previous slide. You just take the tan-h of a Gaussian that is defined by mean and variance, which we got from our network. And the trick is now to sample an additional value, epsilon right here, from a standard Gaussian, and then multiply our variance with this epsilon. And this gives us the function f for our actions right here that only depends on epsilon anymore and not on phi. And using this trick, using this f, we can reparameterize our policy objective by plugging in f for all of our actions. And this now results in the expectation not depending on phi anymore and only depending on our sampled epsilon. And of course, we have to replace all of our actions. And using this trick, we can now compute the gradient with respect to phi, which is this right here. And what this results in is what they claim to be an unbiased gradient estimator. And we can just use this gradient right now to perform some kind of, for example, stochastic gradient descent. And now we have both gradients and both objective functions. Just as a quick side note, the policy gradient presented here is not the actual one they use. They use an approximation given by another function, which they show has the same gradient as the one presented right here, and they also prove this in the paper. But although we derived all those functions, there is still one major problem. And this is that at the moment we're only using a single Q network, which has the risk of overestimating the Q values. And I'm very glad that Jonathan held his presentation last week and explained this topic in great detail and also, in my opinion, very well. So please refer to his talk if you want to know in detail how to solve this problem. But I will still give you a very brief explanation of this overestimation bias. The problem is that Q values in general are very noisy, and our Q target right here always takes the action that has the largest value, as you can see right here, which is usually much higher than the true one due to all the noise. And since Q-learning includes bootstrapping and it learns estimates from estimates, the bias accumulates and results in overestimation. And actually, Hado van Hasselt, who is a researcher who did a lot of work regarding overestimation bias in Q-learning, gave a really good example during a talk in which he demonstrates the problem very well. So if you consider the game of roulette, you have only a single state and 171 actions. So this is this plot right here for the game of roulette. And those actions also include one action that leaves the table and stops playing. And in this setting, you can see right here that the average reward is $0. So the best action to take is just to leave the table and stop playing. But due to overestimation, the Q-learning agent that was trained in this environment estimates the return to be around $23, when in reality it's zero. So the agent just keeps playing and losing instead of leaving the table. And what you can do to resolve these issues is you can use two different unbiased estimates of the Q function. And based on this idea, there are also a few more sophisticated approaches, such as clipped double Q learning. And this was proposed by Fujimoto and colleagues, and is also what soft actor critic, but TD3 is using too. In clipped double Q learning, you use in total 4 networks. You use 2 networks for each critique 1 to get unbiased Q value estimates. And additionally, you use target models also for each critique network, 1 additional target network. And those combined are claimed to reduce variance. And in the following slide, we will see how those networks are used. First, the TD target, Y right here, is computed using the minimum of both target networks. And of course, we take the minimum because we want to reduce the overestimation bias. And after having obtained this TD target, the critique loss function for both non-target networks is then computed as before, just using this new TD target. And additionally, the actor loss function also uses the minimum of both target networks to prevent overestimation bias, just as up here. And in the last step, the target networks are obtained by Podiac averaging over the course of training the Q network parameters from the normal Q networks. And this basically means that the parameters of the standard Q networks are slowly copied over to the target networks. And this tau right here is a hyperparameter that basically determines how fast this copying is happening. And this whole procedure is very similar to TD3, which we've seen last week, although there is one difference, since there's no explicit target policy smoothing, which actually gave me a hard time figuring out what they do exactly. So just as a recap, target policy smoothing serves as kind of a regularizer for the algorithm. And if the Q function approximator develops some kind of incorrect sharp peak in the Q function for some action, the policy will quickly exploit this peak and then become brittle or incorrect, which is just the overestimation. And TD3 accomplishes this or fixes this problem by smoothing and adding random noise to the TD target Y. Actually, they add this to the action and they clip this noise before adding it, and that's why it's called clip double Q learning. But soft actor critic, on the other hand, learns in general a stochastic policy, and therefore those sharp peaks are not a problem at all. And this is because the noise from the stochasticity is sufficient enough to get a similar smoothing effect like TD3 does with this added noise and clipping. So that's why there is no clipping in soft actor critic, although they use clipped double Q learning. So the term clipped is kind of misleading here. Okay, finally, I can show you the complete algorithm and we can put everything together. So here you can see the complete algorithm, and it starts by initializing all of our networks and also initializing the replay buffer. And in each iteration, the replay buffer is filled with interactions, and afterwards we, for example, apply a stochastic gradient descent and start by optimizing our Q functions. This is done like we've seen on the previous slide using the clip double Q learning. And after having optimized those, we also update the policy weights in the direction suggested by the Q functions. And we skip this line for now, but this last line is just a Poliak averaging for updating the target networks of the Q function. We've also seen that in the slide before. And the line I just skipped is actually the temperature adjustment. So the temperature, if you remember, is this alpha that is in front of the entropy term. And as it turns out, soft actor critic is brittle in some cases due to this temperature hyperparameter. And unfortunately, it is very difficult to adjust this temperature because the entropy can vary very unpredictably, both across tasks and also during training as the policy becomes better. So you need to tune this temperature, this alpha, for every task individually. And in a follow-up paper, as I mentioned before, the authors proposed a way to actually auto-adjust this temperature. So what I'm going to do before showing you results of soft actor critic is explain how they were able to learn this temperature and to automatically adjust it. And this is accomplished by formulating a constraint optimization problem right here. And what you want to do is you want to maximize over all policies the expected return while satisfying a minimum entropy constraint, this one right here. And here the lower bound, H0, is chosen by a heuristic that is proposed by the authors, and this heuristic depends on the dimensionality of the action space. And what you usually do to solve an optimization problem like this is you construct the Lagrange expression. And this is this expression down here. And here you include your original maximization problem in this case, and you also include your constraint multiplied by a dual variable. And in literature, this is usually called lambda. And in this case, just to explain this, what you want to do is you want your constraint to be larger or equal 0. So you subtract h0 here from the right side, and you put this down here and multiply it with your dual variable. And if you multiply it out, you get this expression right here. And as you can see, our dual variable in front of our entropy is exactly our alpha, our temperature we want to find, because in all of our derivations, we had this alpha in front of the entropy term. And you solve this Lagrange expression, also called the primal dual problem, by maximizing with respect to your original optimization problem and minimizing with respect to your dual variable, in our case alpha. And what this is doing is this term right here is pushing into the direction of the optimum of our problem, and our constraint right here is pulling away. And therefore you have this constraint right here because in accordance to the KKT conditions, our constraint can either be inactive, so it can be 0, or it can pull away from the optimum and it can be larger than 0. And it can never also push into the direction, so it can never be less than 0. And if you formulate this in an iterative fashion for each time step, you get those equations right here. And you iteratively try to find an optimal policy first with your current alpha. And afterwards, you try to solve your dual problem by minimizing with respect to alpha, and therefore finding the optimal alpha. And because this is the same for every time step, we can formulate a temperature objective that we want to minimize after learning our policy in each iteration. And this is exactly this minimization down here, just filled in with the entropy definition. So this is the entropy definition. And by using any kind of gradient descent method, you can try to find an optimum and minimize this objective function, and that therefore learn the temperature alpha in an iterative way. And you can see this temperature annealing in the results I'm going to show you now, finally. These results are from the third SAC paper, and they show benchmark results from various Mujoka environments. And here you can see SAC with a fixed and tuned temperature in yellow, and SAC with the learned temperature with the approach we've just seen in blue. And as it's pretty obvious that learning the temperature works well in some cases, but in other cases it performs worse than the fixed temperature. But what you also can see right here is that SAC performs quite well, especially in comparison to TD3, which is kind of the direct cotendant to soft acticritic and is purple in this plot right here. But in general, I would not say that SAC is in any way superior to TD3. Both have their pros and cons. But what I find quite interesting is that SAC is still one of the most sample-efficient algorithms. So this enables, for example, learning robotic tasks in the real time without any simulation. And here the authors trained a small four-legged robot to walk. And the policy learned is also quite robust since it's able to walk over various obstacles right here. And yes, I just find this quite interesting. And this has been all from my side. And on my last slides, I just have my references. And I want to thank you for listening. And if you have any questions, just feel free to ask them.